Somebody who's just listening to this lesson, sorry I forgot to record, but here we are in the middle of the notes. That's what the front looks like. It's basically that fluid force depends on depth, weight density, and surface area. The first example is a non-calculus one. Let's focus on the second one. I will encourage you to pause this slide if you're listening at home. Does anybody ever listen to these? I think I have like 0 listeners on YouTube. But that's okay. Maybe my mom listens to them, I think she actually.
You could share this with her.
I should.
And maybe she
Yeah. So at any rate, we are drawing our axis, trying to calculate the depth of each slice, the area of each slice, and setting up the integral. That's where we are here. And what'd you get for an answer, please? Somebody calculated. Or not? 3062.5. In terms of units, the weight density was newtons per cubic meter. What's the depth? Meters. What's the width? Meters. What's the height of each slice? Meters. And so newtons per cubic meter times cubic meters is newtons. All right, so the force is in newtons on the front face. Okay, now, back to the notes I was talking about. When I say those area slices, there are actually 3 cases of area. There is the case where the width is constant, like we just did. There is also a case that we're about to do where the width of each slice, or the base of each slice, varies. Each base is a horizontal distance. What do you call a horizontal distance that varies? We call it just x. Just x. We call it x, okay? It's, 1 wide, 2 wide, 3 wide, 4 wide. Each base is x. The thing is this, though. In these problems, the height is always the slice height, so dy. So when you get that x, you're going to have to put in y terms because the heights are dy. It's always y is the variable of integration. You could also get a figure that has something like this kind of symmetry, in which case the base of each rectangle is definitely varying, but it's not x, it's 2x. Yeah, each width is 2x, and you would have to sub in full x and have it. All right, I have each one of those cases, so let's go on to the next case, shall we? So say you had a trough with a triangular face. I didn't draw the whole trough, but it looks like this. Okay, has a triangular face on the front, and it's filled with gas, and by that gas I meant gasoline. So how much force is exerted on the triangular face? Not on the faces, the triangular face of the trough. Now, first, I don't like triangles that go that way. No offense. I just would prefer it going to the first quadrant. So can I change this and draw it first quadrant, reflect it over? Would the force be any different? Most definitely not. So I'm going to draw it this way. Now, I'd put the origin at the bottom. I think you'll find it easiest if we do, and I'll explain why. But there are a couple different approaches here as far as where to put the origin. It's up to you. Eventually, you'll make that choice yourself. So it says in the directions that the top edge is 3 meters and the side edge is 4 meters, but it's only half full. All that in the directions. You follow? Are you with me? Okay. So then, we want to figure out how much force is applied to that triangular face. And again, we're going to do it by saying, well, how much force is this? Now, I know it feels like now it should be a trapezoid, but remember, it's so thin that it's really just a line, and it is all but a rectangle. So don't worry about using a trapezoid for each slice's area. Rectangle is fine. So let's go there. The force is rho dA, what's rho? They give it to you. 6,600. It's the weight density of the fluid, how dense the fluid is. Oil or gas is a little less dense than water. The depth. What about the depth of each slice? 2 minus y or 4 minus y? It's 2. It's about the surface of the fluid, not about the top of the container. I could make this container 1 billion meters tall, and it's not going to change the depth of each slice. You with me? So the depth is 2 minus y. The area of each, now again, I'm not talking the area of the triangle, the area of each slice that's feeling pressure. What's the base? Constant or variable? Variable. I'm going to call it x, and we'll gradually do this in one step, but I'm going to do it in two. I'm going to say it's x wide and how high? Each slice is dy high. The limits, what are they from?
0 to 2.
0 to 2. All right, now then, what can I put in y's, or x's, excuse me, in x's place? Here's a width, that's x. 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 What do you notice about all those x's? They're always on the line. They're always on the line. All x's are on the line. So I can write an equation for the line. Y equals 4/3 x, so x equals 3/4 y. I can plug in x's place 3/4 y. Slap that in your calculator, call it newtons, boom, you're good. Okay? I trust you can put that in your calculator and push come to shove. You with me? All right. Let's see if you're getting a feel. Try the next one on your own. We'll talk about it. Actually, let's make sure we all draw it the same way so we all have the same setup and we can check our setup. So the way I read it, it's a barrel, which I assume cylinder, full of water, but on its side. So we're looking at this. Find the force applied to the front face of the barrel. Where do you want to put the origin, given that you're looking at the circle as your figure? Center of the circle, beautiful. And the radius is 0.5, and it is full. Now find the force on that face. I'll let you work on that. Oh, sorry. It's really radiate, but if it helps you, you can deviate. It's water again. Make sure you use the right row. Ready? Or not yet? Okay, what's the depth? What did you say for the depth? 0.5 minus y. Do we all agree? Okay, so it's always how far you're going from the surface or the top of the fluid down to some point. So imagine if I said, how deep is the slice here? Well, that slice at negative 0.1 would be 0.6 deep because it's from 0.5 down to 0.1. So it's always the top minus the whatever the y is at that slice we're working. Okay. The area, starting off basic, is it a constant width, x width, or a 2x width? 2x width. There's symmetry to these rectangles. It's an x on either side of the axis, so it's 2x wide. And the height, dy, and the limits? 0 or negative 0.5? Negative 0.5 to 0.5. Now the only thing we have to then monkey with is the x. The 2 is fine. What did you put in x's place? Square root of 0.25 minus y squared. You follow it?
How do you get the pi?
The what?
The pi back here.
This guy? I started with saying the equation of the circle is x squared plus y squared equals 0.5 and solved it for x. So that's where that came from. Sorry, I didn't finish that over. What about that plus or minus? Some students say, well, when you square root, isn't it plus or minus? Doesn't if it's plus, isn't it just this side? So am I just doing the right side that we're worried about? Yeah, the 2. The 2 is doing that. This is, you're right, this is x, but we're doing 2x. So we're covered. We're good. Okay? You follow? Yep. Okay. Now, going a little further, those are the ones in the Saxon book, but again, I don't want you to be at a disadvantage. And so if you'd done this in a college level, like at Mines, that uses the Rogowski book, they would also go on an inclined plane or an inclined face. So how much force, instead of a horizontal face or a vertical face, at a slanted kind of face. So say you had a dam, and it had a 45-degree slant to it, and the face looked like this. This is the face that's feeling all the water pressure. The water is applying pressure to this side. You with me? Cool? And there's some Newton principle that the force is always applying in a perpendicular fashion to the face, but I don't remember that part. Sorry. So I want the total force on that side, on this slanted side. I'll tell you what, why don't you think about that on your own, and I will go over it in a second, but I want the total force of all these bad boys. All those rectangles. Think about it. This one, calculated answer, so we can see at the end if we agree, and let's see what we get. Might help you to draw a little baby triangle. Label the sides. What? You're right, I shouldn't have. It is kind of weird to see degrees, isn't it? It's crazy.
And then you have the same. So I'll just or treat it like it's
It's water. I don't know if I ever said it's water, but I've never seen a dam holding anything but water.
Have you seen it in the ocean? Like saturated?
Are they there?
I just used for
And actually, seawater has different ways different works.
Is this not 30? Is this 30 or is this 30? This is 30 meters wide. Is this 30 meters
I think it has to be the dam is actually this wide. That's why
All right. Chuck, can we do
Oh, unless he wants us to use 45. Slide on. That's why it's like 3 inches. It's like 30 meters wide. I think it's
Oh, I misunderstood it was 30. What is 30?
well, because it can be in it.
It's 30 wide. The dam is 30
I
wide.
know, but what is the wide, like, okay, so that's, yeah.
I thought it was the other one. That's what I said.
Oh, no. No. That couldn't be. I mean, it's a 45, 90, so that couldn't be 30 and that's 50.
That's true.
Oh, yeah. Okay, that makes more sense.
You should get a really large number. In the dam.
Okay, so this is like actual dam. There's no pressure.
Yeah.
Like showing this way.
Forget.
Oh, wait. This is what you're, wait. Oh, I get it, 'cause you're finding the pressure on this. Oh, okay.
Oh, gotcha.
So that would, I don't know. That's fine. That's fine.
Take mine.
Air out.
It's just the area of science.
It's the area. Now, these are still right.
These
slices are still
No, it's not.
The height.
That's not, this isn't 30, this isn't 30.
That's not
This is 30.
But these are these.
I think that the extra 30 is all right.
Remember, you're not thinking the area of the whole
Width is 30 the whole time.
dimensional slices.
Not really sure.
So what's this? When you draw this little slice,
I'm almost certain that's not right. I just
But you just, yeah, you just use a parabolic.
no,
Wait, what?
no. Okay, look at this little slice here. This little baby slice here, yeah? How long is this side?
30.
30. I want the area of this face, yeah? Okay. Don't know this side. I need that side. To find the area of this, I need this slanted side, yeah? What's this? No! Slices!
Wait, what? Oh, it's
You
on the
just
side.
said it was 50.
No, I didn't say this whole thing. I said this little tiny slice. How high is that? dy. So
Oh,
what's
I see.
this?
So now down to dy. Oh.
Now you're making me mad.
Whatever.
Shall I go get an algebra 2 kid to solve this right triangle trig problem for us?
Yeah.
Root 2 dy. No, sine is opposite to hypotenuse. That's dy to question mark. Therefore, question mark is, sorry.
Do you want
Oh yeah, that's right. So I'm right. Question mark is dy over root 2 over 2, yeah? Which is dy root 2. We. Okay, so then, what's your integral? Oh, not by force. 9,800. What's the depth of each slice? The fact that it's slanted means nothing. The depth of each slice is still 50 minus what? The slant comes in on the areas. Each base of each rectangle is always 30. And the slanted side, which is really the height of each rectangle, is always root 2 dy. And so the limits are where the height is, the y is. You're talking about y, and y is just the vertical piece, not the slanted piece, the vertical piece. And so y is 0 to 50.
I was really close. I just put y instead of.
Okay. It's root 2 dy. So that's the way the slant comes in.
Could you also do it where you use trigonometry chem on the outside and you find the force of the vertical component and then divide it by the sine of 45? I got the same answer.
You could do that. I don't know if it would always work, but it seems logical. I agree. So I got something like 1 point something inch, 519 million-ish, or 5.19 times 10 to the 8 newtons. All right, that is that. Boom. Should we go over questions or should we go tests? All right, tests. Here we go. All right, put your phones away. Take your phones off your desk, please. I will need these tests back. I don't know if we'll get to corrections or all the corrections or not, but I'm going to pause.